Welcome to the second day of our conference, the 12th edition of the International Micro-Air Vehicle Conference. And today I am thrilled to introduce you Tom Richardson, who is going to be our third keynote speaker, the first keynote speaker of the day. I'm going to read his biography, but first I want to say thank you to Tom for having accepted to be here with us and to talk about a very interesting topic. I think it's going to be very interesting for us who live here in Puebla, where we have nice volcanoes and mountains. But let me say first that Tom is a senior lecturer in flight dynamics and control at the University of Bristol with a PhD in nonlinear control system design. He specializes in the application of modern control theory and novel sensors to unmanned air systems. Tom has held an NPPL, a pilot license, for over 15 years, runs the University of Bristol glider flight test course, and has been responsible for US operations in multiple countries. He has been granted permission multiple times for beyond visual line of sight, quite impressive, operations, and holds the University of Bristol CAA US permission for commercial operations. He has also run flight demonstrations and test flights for DSTL, BAE systems, Kinetic, DSTL, and Rock Manor. Tom is also a founding partner of Perceptual Robotics, which has already recently been awarded Robotics and AI in Extreme Environments funding by Innovate UK for offshore wind turbine inspection. So after having said that, I don't want to take more time. So please, Tom, go ahead. And once again, you're welcome, and thank you for being here. Please, the floor is yours.
Brilliant. Thank you so much for that. Okay, I need to share my screen. Okay, Jose, could you just confirm if you can see the screen?
Yes, I do.
Brilliant. Thank you so much for inviting me. Thank you so much for having me and allowing me to present to you. It's an absolute pleasure to be here. I've been involved with IMAV for a number of years. I think it was 2005 or 2006 I traveled to the first one, which was in Europe. So it's a pleasure to be here. And I'm going to be talking to you about remote sampling and measurement of volcanic emissions using drones. So my primary research interests are in flight dynamics and control, particularly for agile vehicles. But we do quite a lot of work where we go out and we take our vehicles, our drones, into the field, and we use them to support colleagues, in particular with sort of challenge-led applications. And the one that I'm going to be talking about today is volcanoes, and you can see the Volcan de Fuego on the right-hand side. That's in Guatemala, and that's going to be one of the examples that I talk about today. And that particular image was taken from one of our own drones here at Bristol in a campaign that we had out there in March of 2019. Unfortunately, due to COVID, we haven't actually been on too many campaigns in the last 2 years, but we have recently been out to Guatemala again in October of this year. If anybody has any questions following this presentation, please feel free to email me at thomas.richardson@bristol.ac.uk, and I'd be very happy to answer them for you. So today I'm going to give you a little bit of my background. I'm then going to talk to you briefly about Ascension Island, because Ascension Island was the first place outside of the UK where we took our vehicles and we were applying them to a scientific challenge. I'm then going to talk in detail about Fuego Volcano in Guatemala, and then I'm going to be talking about some gas measurements we did at Manam Volcano in Papua New Guinea as part of a worldwide effort in terms of exploring the benefits of aerial robotics in volcanology. A lot of what I talk about today is some of the challenges involved with taking vehicles outside the country and deploying them in the field and flying them in remote and challenging environments. I'm also going to talk about a lot of the research challenges that fall out of doing this and some of the work that we're going to be doing in the future. The picture to the right-hand side there is of Manam volcano vent. That's in Papua New Guinea, and that was taken on a field trip that we had in May of 2019. And you can see the open vent of Manam volcano. We were flying through the plume, and we are doing real-time gas measurement in that particular plume. So my background is in flight dynamics and control. I've got a pilot license. I run the course here at the University of Bristol. And I've always been interested in taking vehicles outside of the lab environment and challenging them testing them in challenging real world environments. And things that work in the lab or work in simulation don't always work in the field. And it's finding out why they don't work and solving those problems that I find really challenging, interesting, and rewarding. On the right-hand side there is Perceptual Robotics. If anybody is interested, you can search for Perceptual Robotics in Google. But the purpose of that company that we set up with some graduates here from Bristol is using aerial robotics for inspection and maintenance, in this case for wind turbine inspection. One of the reasons why I do this work is the people that you get to work with. And all three of the examples that I give you today came out of conversations with colleagues. So if I have one recommendation for you from today, it's to listen to your colleagues, to work with your colleagues. And if they have an interesting challenge, to go and work with them to see if you can address it. The second recommendation is to learn a little bit about geography, because in all three of these cases, it was places that I hadn't heard of before, actually, before I went. The first one was Professor Jim Freer, who until recently was a professor of in geographical sciences here at Bristol, and he asked me if I knew where Ascension Island was. The answer is it's in the middle of the Atlantic, and I'll show you some slides on that in a moment. And he asked me if I was interested in using aerial robotics for atmospheric sampling above Ascension Island. And my answer was yes, of course. The second one that I've got there is Matt Watson, Professor Matt Watson from Bristol, Earth Sciences. And he said, do you know where Fuego is? Fuego is the volcano in Guatemala. And he said, I would like to sample ash from inside an ash plume over the top of Fuego Volcano. And the third one there is Dr. Emma Liu from UCL. He's a lecturer at University College London. And she said, do you know where Manam is? And the answer is Papua New Guinea. And we did the real-time gas measurement over the top of that particular plume, or within that plume. And so the first set of thanks I'd like to say is to all three of these people for involving me in their work and offering me a challenge. And from the engineering perspective, there is nothing better than a science-led or technology-led challenge from which we can draw on our own research. So the first one of those three examples I'm talking about is in Ascension Island, and the challenge was atmospheric sampling. So we did this between 2014 and 2016. We traveled there 3 times. We built 3 multi-rotors. Sometimes in these challenges, people have a preconceived idea of what the best way of approaching it might be. And actually, we went through 2 or 3 different iterations and different approaches to doing this. The one that we decided on in the end was to fly multi-rotors up, and we needed to reach in the region of 2,000 to 2,500 meters above ground level. And then we took samples within, and you can see on the left-hand side there, you can see a drone there with a sample collection bag underneath a Tedler bag that we inflated at altitude, and then that air was taken back to sensors in the UK, where they were tested for the content of those samples. We ended up in doing over 100 sample flights to altitude and collecting a number of different samples. It was great in the end. We won an award for doing this from the engineer, and there are a number of publications on it. And as we go through this presentation, I've highlighted some of the publications that we've had as we've gone through, so feel free to look those up. The challenges of flying outside in these kind of atmospheric conditions was highlighted to us. One such example, you can see on the right-hand side there, there's two plots. They're both on the same day in 2014. One was taken at 12:41 in the afternoon, and one was taken at 2:36 in the afternoon. And you can see the prediction from the Met Office, given by the green dotted line. And you can see the solid dark green line. This is in terms of wind speed as we climbed up through 2,000 meters and went up to about 2,300 meters. And then you can see that actually the Met Office prediction hadn't changed much, but you can see the actual real world environment had. So working off the forecasts, up close on to 2,000 meters, we had 40-mile-an-hour winds at those kind of altitudes. So operating vehicles, and this is beyond visual line of sight because we couldn't see the vehicles at these altitudes, remotely reacting to the conditions that you're in and learning to generate flight plans and operate the vehicles in really quite hostile conditions is part of the process, and a really interesting and intriguing one. The other part of doing these kind of deployments is they're usually in the middle of nowhere. This was the site of operations that we had on Ascension Island, and we went out there, as I said, 3 times. And we were flying from this area here, which we picked up on a previous trip that we went out, and we looked all over the island for the best place to operate from. But it's not easy in terms of flying your equipment over there, in terms of deploying it and flying it repeatedly and safely in order to collect the data. But it's worth doing. By the way, the reason for doing it in Ascension Island, which I skipped over completely, is that Ascension Island, being in the middle of the Atlantic, has air masses that is coming both from the South Atlantic and also from Africa, depending on the altitude at which you're at. So you can actually sample different air masses by taking samples at different altitudes. And that's the reason why we were over there and why we were flying. You can see some of the results from the tests and the samples we took on the right-hand side, and you can see the ones in the South Atlantic air have a different composition from the ones in the African air above. So in terms of proving that the system worked, it was a great success, and also in terms of the science that we got out of it, our colleagues were also delighted with the results. From the operational side of it, one thing to highlight is that we were operating on Ascension Island, which comes under the Civil Aviation Authority rules and regulations, although a slightly different department. But we needed to get clearance from the CAA, brackets ASSI. We were also operating within 3 nautical miles of a US airbase, which provided its own challenges in order to get clearances. So another part of doing this work, which is really quite challenging, is liaising with the appropriate air authorities and also with the appropriate local law enforcement authorities, etc., to get permissions to do it. And so that's definitely one of the takeaways from this that we took forward into the other work. So that's really the first example of where we went overseas and we did this kind of work. The one I'm going to talk about now is Volcán de Fuego. So you can see a picture there on the right-hand side of Fuego. This picture is taken from the Volcanology Observatory. And you can see it erupts. And the beautiful thing about Fuego Volcano is it erupts about every 20 minutes to 30 minutes. And you get this ash plume that comes out of it. And then it drifts downwind. And gradually the ash falls out as it drifts downwind. And the composition of this ash plume changes. So Matt Watson, who I mentioned to you before, we stood together at the bottom, we looked up towards the volcano, and he said, can you fly your vehicles up through that ash plume, and can you get me a sample of the ash that is up there? So bearing in mind, if I go on to the next slide, that the observatory is down in the left-hand corner here. We were looking up towards Fuego, and the distance is around about 8 kilometers, and the height gain required, and I'm mixing my units here, is 10,000 feet, so approximately 3,000 to 3,500 meters change in altitude and about 8 kilometers. So that's true BV loss operations there. So I said yes, and we went ahead and we made plans to do this. And I would like to take this opportunity of thanking several people. Here in the UK, we have the Research Council funding bodies. EPSRC funded this work through the Cascade program grant. So the Cascade program grant is 5 universities over 5 years, addressing a lot of the challenges involved with UAV or drone technologies and research. So it's funded from EPSRC through Cascade. I'd also like to thank DJAC, which is the air authority within Guatemala, who have been absolutely fantastic in supporting our work and working with them to get the correct permissions to do this. I'd also like to thank INSAVUME, which is the volcanology government department responsible for monitoring the volcanoes, and it has been a great pleasure working with them in order to try and support their efforts in understanding the volcano and understanding the risk that comes with it. There's also been a very large number of people involved in this work locally at the university who it has been a pleasure working with. So we put it in as a case study, a sample of volcanic plume within the Cascade case study list. And then we went out to Guatemala and we started to operate the drones. So we have flown, this was a fairly early picture on the left-hand side, you can see here. And we've flown a number of multi-rotors, both from a Catenango nearby, but also fixed wing, and here are 2 of the fixed wing vehicles we've been flying from the observatory up to Fuego and up towards the target. So the target here are these ash plume, which as it erupts, you can see this is from the most recent one, this is from the eruption before, and the eruption before that. So you're working remotely and you need enough information to tell you about the plume, to know when you're in it, to plan your flight into it, and to respond in real time to what's going on. This is an interesting short animation here, just to give you an idea of the power of drones, in speech marks, in terms of how they can support the work of INSAVUME. So this particular 3D model was generated from data from 2 cameras on board one of our vehicles, taken over the course of around about a 45-minute flight. And it covers an area that's around about 8 kilometers by 10 kilometers. And you can see the level of detail that is involved in here. So the ability for drones to capture detail in high quality data is absolutely fantastic for the purposes of INSAVUME and for monitoring the volcano. And just to go back to the reasons why we're doing this, as well as providing a lot of engineering research challenges, it also, in trying to help understand the risks, it can help support the local people. Within about 20 kilometers of the top of this volcano, you've got in the order of 100,000 people living. And unfortunately, 2 years ago, they had a pyroclastic flow which came down one of the barrancas, which I think it was this one, it came down. And unfortunately, a large number of people lost their lives in one of the villages. So that's the motivation for doing it. In addition to that, this particular volcano is within about 45 minutes drive of the capital city of Guatemala. And so it's like having an active volcano within Reading in close proximity to Heathrow Airport. So it obviously has a significant impact on their ability to fly international flights in this particular direction. So that's the motivation for doing it. Going into a little bit more of the engineering. So in this case, we needed to take samples. We created this means of collecting them. So these are what we call ash plume stub holders. And these stubs on the left-hand side, they're used by the military in the UK for collecting samples of aircraft and other vehicles. They're really quite small. They have sticky pads on the front of them. So we developed this mechanism to allow us to deploy them in flight. And you can see these mounted on top of the vehicle prior to launch. So we were collecting those on these stubs, and we can bring those back and use them with the electron microscope that we have in Bristol to analyze the ash that we collected. So concentrating on these, they're based on an X8 airframe. Wherever possible, we buy in airframes and then we fit our own avionics and write code for them. Just a side note, recently we've started developing our own vehicle because we haven't found a vehicle yet to buy in that meets our performance requirements that we need, both for this particular volcano, and actually I was talking to Jose just recently, one of the volcanoes in Mexico is going to be a brilliant target for doing some of this work on. So I very much look forward to collaborating with Jose in that area. And for those purposes, we're developing our own vehicle. With these though, your takeoff mass is around about 4 kilograms. We've looked at various different battery chemistries and types. We've had a maximum of about 75 minutes in flight, together with the sensors that we're carrying on board to fly there. Bearing in mind, it takes you in the region of about 20 to 25 minutes to climb up to altitude and to get to the top of the volcano. So that will leave you in the order of about 25 to 30 minutes to operate up there before you need to come back. So you're operating in the field, and you can see on the right-hand side there, that's the sort of base camp that we have and the kind of setup we have when we're operating. The other great thing about doing this work is that it involves teams of people, and I absolutely love working with great teams of people. So at a very minimum with this work, we tend to have 4 people. We would have 2 people on the launch and the recovery, and then 2 people on the flight operations. And you can see the takeoff of one of these vehicles and the kind of environment in which we're flying when we're doing it. We tend to push the platforms themselves to the limit. And you can see here at takeoff, sorry, you can see here at takeoff, with the lithium-ion battery setup that we've got, and it tends to be the takeoff that's a limiting factor because we're already at 4,000 feet and it tends to be quite hot there, so the performance of the vehicle comes into play as well. So the question is, how do we target the plumes? So this particular picture, which is the first one that I showed you, is taken from one of those particular aircraft. In this case, it's heading towards the plume. The thing about the plume is you don't know it's going to erupt as you take off. You know it's going to erupt at some point, but you don't know exactly when it's going to erupt. So the protocol that we got into was to take off, to place ourselves relative to the summit, somewhere that we could watch the activity on the volcano and we could react to it when it did actually erupt. Which takes you on to the interesting question of, you know, what level of autonomy do you want these vehicles to be operating at? So it's, as you know, relatively simple to have it fly a series of waypoints, and you can see that's what it's doing here. We're flying a series of waypoints in this zigzag as we go up. There's several reasons for doing that. One is you don't want to climb up in the lee of the volcano because we are downwind of the volcano summit. So you want to stay away from the air that's just down from the summit because it can be very difficult to climb up into. Second thing is you want to operate your vehicle at the most efficient climb rate. So you want to use the minimal energy possible that is required to get to the top. You can actually see on the way back, spiraling down. Obviously, when you're coming back down again, that doesn't apply. And you can actually glide all the way from the top, all the way to the bottom here over 10,000 feet and 8 kilometers. You can also probably see on this figure here, there's this kind of pink line here that is being flown in the fly-by-wire mode. If you're familiar with the RGplane software, then we're flying at a fly-by-wire mode, which allows our PhD student, Ben Schellenberg on the right hand here, to actually fly remotely and target the plumes that we're interested in. So this is a fairly early flight where we're flying up automatically, and then we get to the point where we want to fly through the plume, and Ben takes over and flies it in a fly-by-wire mode in order to collect the sample, and then we automate the recovery. So in this case, pilot workload requires some level of autopilot involvement. Automation is desirable there, and that's where we're heading with this work, and one of the main aims to fully automate this process. The reason being is the more that we can automate it, the more we can hand it over to other people so they can also use the same techniques. So how do we know if we're in the plume or not? Visually, we can detect it, and you can run algorithms that can look for plume and can visually detect it. It's also good to know when you're actually in it. And here is some data involving temperature and humidity. This section in the middle of the flight is actually when we're within the plume. And you can see there are changes in temperature and humidity there that are quite characteristic of being in the plume. The other thing that's interesting is that you get, this is flight data off a flight, you tend to get a drop in the throttle required because there tends to be rising air in these plumes. So the vehicle is naturally trying to rise, but you're trying to maintain altitude. You also tend to get increased level of turbulence when you're within the plume. And so we've come up, there's a paper that we published where we were looking at the combination of the temperature, humidity, and also the flight data on board in real time to detect confidently when we're in the plume or not. And the idea behind this is that if we can do the detection automatically, we can start to do the flight planning automatically as well. This is a video of, I think this is the first time that we actually flew through a plume. We were quite cautious in the early stages of the plumes that we were flying through. And you'll see you lose slight visibility. It becomes a little bit more turbulent. The aircraft is correcting. At this point, we would have the stubs open and we'd be collecting samples. And then we close them as we came out the other side. So that's a fairly light plume, and we're just glancing the edge of it and capturing samples. And one of the great things, again, about working in a team, we're working with people. In this particular case, we have Matt Watson there, the volcanologist, who gives us a lot of real-time feedback about what we're looking at, because we've got real-time video coming down to us, and we can actually target in real time which part of the plume we'd like to sample. So one of the lessons coming out of this is there is really tight collaboration between the pilot, and we do still have a pilot in this case, and we have ground control that is studying where the vehicle is. We've got a ground control station here, but also we've developed our own what we refer to as widgets, which tell us specific information about what we're looking at in the plume and gives us data in the flight compared to previous flights in particular. So when you're doing something and doing it repeatedly, you get better at doing it. And so when you're comparing your data to a previous flight, you can make a decision very quickly about what you need to do. So we have ground control working closely with the pilot and obviously with the drone that is flying. So the sort of next stage in this is, this was quite a neat point where we actually created ourselves a rally point near to the top of Fuego. So we climb up towards it. And then these pink sections here, each one of these is passing through another plume. So we're going between the automatic waypoint following to Ben taking control of it, and flying through the plumes themselves for the purposes of the ash collection. And if you do this repeatedly, and we did it repeatedly for about 10 days in 2019, building up experience with the aircraft, building up experience with what we were trying to sample, then you find generally you get better at doing it. The resolution isn't particularly good on these, but we did 39 flights over about a 10-day period. Actually, that should be 2019 because these were carried out 2019. We looked at 2 different battery chemistries, but you can see generally the flight time that we're having in the air increases, and the time above the summit increases as well, in particular with the different battery chemistries that we've got there. So this was one of those flights in 2019. The size of that plume, it's probably up to about 1 kilometer in height at its greatest extent. And you'll see as we fly through the bottom of this, this is around about, oh, this is at 18,000 feet, which was the upper of the limit of the flight envelope that we had. And you can see us passing through the bottom of that plume. You might, if your screens are good and you're getting the bandwidth, you might even see some of the ash passing down over the vehicle as we fly through it, and we're taking these samples. So by the time we got to doing this flight, we were quite happy to fly through some really quite turbulent plumes, and we collected a large number of samples. What was also interesting is that this particular plume, we got samples from within the plume itself, but we also had samples of the ash falling out over ourselves and over the village that was just downwind of us. So we could look at what we collected within the plume in conjunction with what was collected as it fell out. So as we move towards fully autonomous flights, this was a flight that we did in that campaign as well. And what we did here, it doesn't look particularly interesting, but it's quite exciting because as we took off, this was the target altitude, the vehicle took off, and as it translated across this leg here, it optimized the route to the top. So the previous flight plans you've seen were ones that we came up and we generated by hand. In this case, this particular trajectory is generated on the fly after the vehicle is taken off. The reason for doing this is it takes us closer to where we want to be with the autonomy side. And the next challenge that Matters has given us is to capture the same plume, both proximal and distal to the vent. So we're going to tie together the automatic detection of the plume, automatic detection of being inside the plume, together with real-time flight planning whilst we're up there, in order to target the same plume in 2 different positions. And this helps them understand how quickly the ash is falling out and the composition of the plume, both close to the vent and further away as well. So that's where we're going with that particular work. So I'm going to move on to 2 other applications of aero robotics in volcanology that we've been involved with. This work here was carried out by Dr. Kieran Wood, one of the team here in the flight lab at Bristol. And this is using imagery from drones or aero robots to look at plume volume calculations. So this was from a single flight, taking a series of images of the plume. This is obviously a plume coming out. This is a gas plume as opposed to the ash-rich one that we were flying in earlier. So it's a different type of volcano. But if you have imagery, ideally from multiple vehicles at the same time, but it can be of a plume that is relatively constant in terms of the temporal variation, with the same vehicle, you can process the data and you can work out an exact volume of the plume. So we did this first with static cameras from the ground, all aimed at Volcanic Fuego, and worked out the volume of this particular plume. And then we carried it out with imagery that we took in flight from a vehicle. And so having the plume from different places, Kieran has written some brilliant software which calculates the volume of the plume and allows you to understand the size of it, the cross-sectional area, and actually with certain cameras at different wavelengths you can understand the composition of it as well. So that's the target of this work, and there's a couple of papers on there again if you're interested in extracting the volume and understanding the composition of what's in there. And then the last application I'm going to talk about, which will take me from Central America to Papua New Guinea, is in-plume gas measurements. So this was carried out again by Kieran Wood from our group here at Bristol, and in conjunction with Dr. Emma Liu, who I mentioned earlier from UCL. And you'll see two early examples of this on the left-hand side, and this was testing over Bacaya. Actually, that's Fuego there, but this was Bacaya, both of these in Guatemala, with real-time gas measurements. And this is a slightly larger vehicle with a different set of sensors, but doing the same things. It's measuring SO2, H2S, and CO2. So based on this experience and the results that we got from there, we were invited to take part in a project that was led by Dr. Liu, which was called Aerial Observations of Volcanic Emissions Using Unmanned Aerial Systems. And this was funded by the Deep Carbon Observatory. And it was looking at this particular volcano, Manam, that is in Papua New Guinea. It is an island volcano off the shores of Papua New Guinea, relatively inaccessible, and actually it's been studied, but relatively less so than other volcanoes. So you'll see a list of people that are involved at the top there, and again I refer you back to my previous comment. One of the brilliant things about this is working with people, and in this case it was people from all over the world, from University of New Mexico, Michigan Tech, Costa Rica, Papua New Guinea themselves and the local volcanic observatory, Palermo, Germany, and where we've got Chalmers University, and also ourselves here in Bristol and Cambridge University. So this team, it's called Above, went out and studied Manam volcano. And the challenges of operating these vehicles. On the top right, you can see the largest flat area on Manam. And that was both our takeoff site and our recovery site. So that gives you an idea of some of the challenges and of where we were working. And then we're also flying over a highly active plume, and you can see that in the top left-hand side of this. High exit velocity of the plume there. And relatively high and inaccessible from anywhere else on the island. We had an absolutely brilliant time there. The local villages were absolutely brilliant. They welcomed us. You can see my colleague Jim Freer taking part in the welcome ceremony that we had there. And it was brilliant working with them and finding out more about the volcano and the risk and the threat that they live with daily there. So we flew over the plume, and you can see here that you can see the crater itself, magma at the bottom. This was taken from one of our vehicles from a downwards facing camera we've got there. And we were flying through the gaseous plume here, which starts, and we flew directly through that. And we got the highest measurements I've ever seen of certain gases within that particular plume. Highly energetic, high exit velocity, interesting airspace in which to operate. And we've got the main crater and the plume itself that we were targeting. And again, there's publications if you're interested in doing that. So really to wrap up, I've got just a slide here which I'll go through relatively quickly, but if I've learned a few things from doing overseas field trials and becoming involved in these challenges, these are the things that I've taken away. Manage the risk, safety is paramount. Safety is at the heart of everything that we do, and we work closely with the local air authorities to get the permissions and to maintain our safety when we're out there. Do your homework, collaborate closely with local people and institutions, along with the team. Working with local people and institutions is one of the great benefits of doing this work, which I love doing. Multiple deployments, you never get your best results on the first deployment, just as your simulation never works perfectly the first time you run it on your computer. So if you can afford it, have multiple deployments and include what I call a recce trip, which is a trip to go and see the challenges without the pressures of actually operating. Do the paperwork and preparation before you go, travel lightly, and take everything with you. Don't send it separately, because that can be a problem. Team working is the benefit, and look for complementary skill sets. Have a clear test plan, but be prepared to be flexible, and definitely don't invite the cameras on early trips, which is what we did once, and that was a mistake because they capture all the frustrations of what we do. But those are the main takeaways that I've taken from this. Our future work, the areas of research that we're particularly looking at are in autonomy and the human-machine interface, and that goes as far as control and real-time planning. And I'm really interested in tying in the sensors very closely between detection, identification, and route planning. So we're going to be looking closely at that. Physical interactions with the environment, where we actually deploy sensors, pick them up again, and that leads us on to multiple robots, including aerial, but also ground robots, to study particular targets of interest. So that really takes me to the end, Jose, which I think is around about the 42-minute mark. I've got some pretty pictures here to run. If anybody's got any questions, I'd be delighted to answer them.
Thank you, Tom. A brilliant talk, very nice, quite interesting. It would be very, very nice to have you here to fly over our Popocatépetl volcano, definitely. So please.
I'd love to come.
Yeah, definitely. You're welcome, more than welcome. So please, members of the public, if somebody in the audience wants to make a question, you can write it down in the chat. You can send it to me, and I will read it to Tom.
That would be great. Thank you.
So in the meantime, I want to stay with this point that you made about multiple robots. And certainly you could use ground robots and combine with fixed wing drones. But I was just wondering, what are your thoughts on using maybe not quadcopters, but octocopters? So basically all these multi-rotor vehicles. Is it possible? Are they reusable in this scenario?
Okay, so most of what I've shown you has been fixed wing flying from the observatory. Just go on to the last slide here. But it is possible to fly multi-rotors across Macatenango at Fuego, and the distance is 2.6 kilometers and the height gain is about 200 meters. But you're flying round about 3,800 meters above sea level. So the performance drops off a little bit there. The distances are okay, but the flight times are reduced. What we're going to be doing in January, because we're going back there in January, we'll be starting to deploy sensors and to recover them as well. So because the multi-rotors can't remain in place for long, there is a lot of scope for deployable sensors, and those include ground robots that can move as well in these environments, because there is benefit to moving. So there is a role to play, certainly up to the altitudes that we're looking at here. Beyond that, multi-rotors do struggle, so some kind of mixed mode vehicle or fixed wing is probably more appropriate higher up.
Okay, because I was wondering whether we had this idea of how do you call it, like a mothership. So you have like a large airplane, and then you take on board tiny robots like multi-rotors, because obviously if you want to take a multi-rotor from the ground to the top of the volcano, maybe you will run out of battery. But if you just drop them, and maybe multi-rotors are, they could be more stable on hovering. So I was just wondering whether that would be something useful.
Yeah, definitely. Both in this volcanology work and also we were talking earlier, Jose, about the conservation work. I think having a larger vehicle that can deploy over tens or hundreds of kilometers that can take smaller ones and deploy them and recover them, absolutely. I think there's a lot of applications in those.
Okay, we got some questions. So there is a question saying, asking, was it difficult to get flight authorizations?
We've done it in multiple countries, and some countries are more difficult than others. It can take some time. I would recommend at least 6 months before you go anywhere, broaching the question of flight authorizations. The more you go back to a place, the more they understand what you're trying to do and the better case you have. So establishing a longer term connection, which is what we've done with DJAC in Guatemala, and they've been fantastic. So they understand how we operate, we understand their requirements, and we work with them. The other thing that is good is having quite a good track record. And you've seen images from Guatemala, Montserrat, Chile, Papua New Guinea, Italy. You know, there's a large number of countries you've flown in, and being able to show that you can do it safely in those countries helps with making the case and a good safety case to the air authorities. But it can take time. It shouldn't be overlooked because actually, at the end of the day, you want to be safe. We've only ever lost one drone, by the way. There's probably another question in there somewhere. We did lose one in Papua New Guinea. That plume coming out is highly energetic, and we hit it on a particularly energetic day. So we have lost one drone, but it was intentional to fly into the plume. But it's good to have a safety record, good to talk to people, and good to really plan what you're going to do.
So when you apply for the permissions to fly over, are you required to get a license, or because is there any international organization giving you these type of licenses? I mean, apart from the license for flying, of course, but that you are authorized or you have the credentials to know what you are doing with volcanoes. Is there something like that?
There's nothing internationally, but obviously we have permissions with the CAA here in the UK, which we put forward and say, we have these permissions in the UK and this is how we operate and this is the safety case. But every country tends to vary in terms of what they need and also what they can grant you. So it's really working with every air authority and their requirements. So the ones in Italy are very different, for example, to the ones in Chile. So everyone at the moment needs something different. But the starting point for us is, what is your safety case? How are you going to work when you're out there? We are insured, by the way. We're insured worldwide for drone operations. So that's a key thing as well. And also here are some publications and a previous track record of what we've done. And that sort of opens the conversation, and then we see what locally they need in terms of meeting it.
Great. So there is another question. Which is the minimum aircraft weight to fly around the volcano?
If you want to go and take some good imagery, then DJI Mavic 2 does a beautiful job from the Catanango. So whatever the mass is of a Mavic 2 or Mavic 3 now. In terms of fixed wing, you probably wouldn't get up there for any meaningful time with anything less than about 4 kilos. The vehicle that we're designing at the moment will take off at 16 kilos. And the reason for doing that is we want to carry larger payloads, and we want more performance in terms of the flight envelope out of the vehicle. So for our purposes, between 4 kilos and 16 kilos is what we're looking at currently. I haven't seen a justification myself for going larger than 20 kilos at the moment, because also as you increase the aircraft mass, the risks involved with that vehicle increase. Yeah. So that's the range that we're looking at the moment.
Okay, thank you, Tom. Another question: did you control surfaces or motors? Did your controlled surfaces or motors be damaged by ashes? Okay, so
good question. Okay, multi-rotors, if you fly them through volcanic gaseous plumes, they destroy them very quickly. So they're very acidic. And so the lifetime of a multi-rotor drone in a gaseous plume is really quite low. In terms of a fixed wing, you'll notice on the X8s there, it has a pusher configuration. We've had the vehicle come down completely covered in ash, and the motor doesn't worry about it at all, because it's placed behind the fuselage, so it tends to be in relatively clean air. Bearing in mind also that probably the maximum number of flight hours you put on any vehicle is probably less than 100. So we're flying really low flight hours. And if we notice a problem, we replace them. We have not lost a vehicle in flight because of ash. And we're very careful. We approach things progressively as we go through.
Okay, great. So talking about, or coming back to this point of the multiple drones, because when you show this reconstruction of the ash cloud, which I think is quite nice. So how many do you think you will need to get the better data? So how many drones?
The plan in January is 6. So
okay.
that plume from 6 different viewpoints will give us a really, really good reconstruction, I think. The quick answer is the more the better, but we think somewhere between 4 and 6 gives you the benefit of having multiple drones out there. But so 6 would be my starting point.
Okay, but then how many pilots do you need?
That's an interesting question as well. So, in terms of getting permission to fly, who is responsible for each vehicle? It is the pilot at the end of the day to do that. So the kind of flights we're talking about doing with these vehicles are fully automatic. So there can be intervention from a pilot, but it's not necessarily needed. So the question is, can you present a safety case that allows one pilot to look after multiple drones? Or do you need one pilot per drone? The answer for January is we will have 6 people there who can all fly drones. So we'll have one pilot per drone. But the long-term answer is definitely multiple drones, single pilot operation, and to be able to establish the systems and the safety cases to allow you to do that. But it's being done, as we know, with some of the aerial displays anyway. The aerial displays of drones, so people are doing that. But it is part again of the safety case that you make to the local air authority.
Yeah, definitely, and because then you're talking about potentially a swarm of drones, and then you have all these challenges in robotics, right? Like you want to avoid them to collide with each other. You want them to cover the surface in a smart way. So then, yeah, you have to implement all these robotics techniques, right?
Absolutely, and down to our first flights will be pre-planned, but you want them to be able to respond to what's going on in the environment in real time. So that's where I want to go with this. Great.
So, and another question, apart from, well, you got quite a lot of knowledge on how to do this with the volcanoes. I don't know how many researchers can be as specialized as you are with this application. Is there any other application where you could take all this knowledge and apply it to another type of problem?
Absolutely. In terms of operating in harsh and difficult environments. The other thing that's really nice about, as we're looking here on the screen of Fuego and the environment around Fuego, is that we have the airspace open to us, because actually not many manned aircraft are going to want to fly this close to an active volcano. So when I was there a few weeks ago, I noticed in the program for later on today, you've got wind measurement using drones. Mm-hmm. So that's something we're really interested in and working with the Met Office on. So we were doing some high altitude flights with radio sondes, and we did them close to the volcano here. So applying it to meteorological applications, applying it to different environments. And I mentioned conservation is a really interesting one for us. We talked about previously radiation mapping in Chernobyl. That's something that we've done, which has been really neat. So anywhere that you have a harsh and challenging environment, pollution monitoring, visual inspection of offshore oil rigs and those kind of things, all can learn lessons from what we've done here, and we're looking at different environments so we can apply what we've learned. So it's great working with the scientists, but I think drawing some of this out and applying it commercially is also really an interesting area I'd like to go to. Definitely.
Well, with that, Tom, thank you very much indeed. We are very happy, well, the organizers and I personally on behalf of the conference, we thank you for this very nice presentation. I don't know if you want to say a last message to our audience.
I'd just like to thank you all for your attention, and thank you again, Jose, for inviting me. IMAV is a fantastic conference, and it's a great pleasure to be part of it. So thank you very much.
Thank you, Tom, and thank you, everybody. So with this, we finish this keynote presentation. I didn't introduce myself at the beginning. My name is Jose Martinez Carranza. I am the general chair of this conference, and I had the privilege to introduce Tom, our keynote presenter. And now we have some